In some cases, not. But the bottom line is, from there on, so BL is my nomenclature to stand for boundary layer moving on forward. So fully developed flow represent the boundary layer. Finally, from all the perimeter wall, finally meet. And the entire pipe internally is now influenced by viscosity. The implicit core disappears. There's no longer a flat top velocity profile. All right? That's anything downstream of that is what we call fully developed flow. And the implication is that profile will persist. And it doesn't change anymore in the direction of distance. In other words, if I cut the pipe 10 miles downstream, the velocity profile will look exactly the same. We'll call it fully developed. Yes, questions?
Yeah, in your entrance region outside of your boundary layer,
Yep.
Does your flow exhibit parabolic behavior there?
No. The region outside of the dash line, in this implicit core, because it's not being influenced by viscosity, is always still uniform, constant. Yes?
Is this something that, like, in theory, never actually happens?
No, it does. Why do you say that?
I just thought if it was like a converging thing, like, does it, in theory, like, never quite get there, but practically it does?
No, it does.
Oh, it does.
Oh, it does. Yeah, this entrance region is no more than 8 to 10 diameter from the entrance region. It always becomes fully developed. It's actually a very small segment. And it's most problem we deal with at this level, we don't even care about it. We'll always assume the flow is fully developed. But the application in life that this is the most important region. Case in point, the inlet for aircraft engine. That's a pipe, but it's all entrance flow. It never fully developed. And as an engineer, you have to account for that. All right, I see some conceptual problem here, so let me slow down and make sure you understand what this implication is. Yes?
So is this entrance region, is that like a form of turbulence?
No.
Or is it not?
Again, it depends on the Reynolds number. It depends on where you start. The boundary layer is developing. You start from 0 at the entrance and it gets thicker and thicker. So at some point it may become turbulence. But when and how is beyond the scope. Right? Okay? So yeah, it also relates to the 2300 criteria, but there are other factors that come into play also. Does that make sense? Yeah?
Could we apply Bernoulli inside?
Yes, it's a very good observation. If you are in this implicit core, and that's what all this will actually revisit this in external flow, which is flow over wing or airfoil. If I'm outside of the influence of the boundary layer or the viscous effect, I can use Bernoulli. I can use Bernoulli from here all the way stay in the center. Yes, and people do that. People do that. Yes?
What if you have a changing diameter?
Oh, that's a different problem. No, it's a good problem. I mean, we'll deal with that at the very end of chapter 8, when it goes from bigger to smaller or vice versa. And what happens is there are something called fold separation that can create some pressure drop, and you have to account for that, not from the Moody diagram, but by other means. So we'll talk about that. So it's just sudden expansion. You do that on all plumbing. No plumbing is constant diameter from Alaska to Seattle. No way. I mean, there are valves, there are inlet, there are other reasons that you have to change the diameter. But for the start, we do it only constant diameter first. Right? Yes?
I think I worded my question a little bit incorrectly, but when you're within when you're outside the implicit core, is
Yes.
that parabolic then?
When you're outside the implicit core, which is in the boundary layer, right? This velocity profile, all right, can be parabola, can be what we call 1/7 law. We need the velocity as a function of the distance is raised to 1/7. It's become now a very peculiar condition of the Reynolds number. The shape of this velocity profile, you have to tell me more information, like the Reynolds number. Then I can tell you from previous experiments what that profile looked like. It's nothing but uniform. At this level, that's what I want you to remember. And in some cases, for simplicity, we assume it's linear, which is a simplified version. But as long as you remember it's not uniform, I'm happy. Right? Whether it's linear, parabola, hyperbola, that's detail. Yes?
How does the velocity of the inviscid core compare to the maximum velocity when it's fully developed?
Okay, that's a very, very good question. That's a million-dollar question I'm trying to avoid, but since you asked, I have to answer it. Right? So I want you to think very carefully. Think very carefully. I come in at 10 feet per second, uniform. I'm now at the station 5 diameter downstream, and the profile looks like this, where I have some non-uniform boundary layer. The velocity that is a function of radius. Then I have a core region that the velocity is uniform. I think what you're asking in a simpler term is, what is that velocity in the core region? Is it going to be equal to, greater than, or less than one of the three? And how do you answer that? Is that what you're asking?
Yeah.
Yeah, okay. So I have to answer it since you asked. Tell me what equation you use to answer that. Very good, continuity. No Bernoulli, no energy. And what can you conclude when you use continuity? You got it? Okay. Just that simple.
Wait, it is greater.
It is greater. It has to be greater. Do you remember? Have you done this homework? Think about, have you done this homework? Anyone want to say no? I'll bet you lunch. Have you done this homework? Yes or no? In what chapter? And when? Have you done this homework? You don't remember? Go find out. Go find out if you're going to quiz on Thursday. Go find out, I'm serious. I want to always revisit what we've done before. You have done this homework. Okay? This is why I want to bring it back to a month ago. Go look up the homework specifically for this problem. Go on.
So I was actually asking, whenever you compare the velocity of the inviscid core to the maximum velocity when it's fully developed,
Yeah,
then it would be less than the max when it's fully developed,
Yes.
right? Okay.
correct.
So it would like continuously.
It's all continuity. Okay, I'll give you a 2 minutes break while you raise the board. And when we come back, we have to move on to the energy equation, because that's part of your homework.
Yeah, like the velocity of that center line.
Dr. I forgot to tell you, do you want that, on the side, in the next class? Next class?
Also, like, you just think about this. You have,
It's a function of the diameter.
if you take some away from the other, so then the end is less.
Yeah, that's what there's like.
I am not.
No.
The diameter.
So you're saying that area differently. So like, so that area stays uniform. So like that area, and then on everything is just flat. Everything outside of that area is less. So it's got to become a slack, literally.
Because I do need to cover enough to, so that you have a chance to do problem 814. Let me lay out the problem as a backdrop and motivate why we need the energy equation. So this may be a good place to put in perspective why we need the energy equation and how it's going to help us to solve particular class of problem. So your last homework assignment is a very simple problem. And it's only qualitative, no calculation actually really needed. So you have this problem where you have a pipe with changing elevation between point A and B. You are told at point A, pressure is 32, and it's a lower elevation. At point B, pressure is smaller, couple psi, but the elevation is higher. Can you tell me which way the flow is going? Up or down? I have half up, half down. Democracy of Bernoulli. Oh, very good. Bernoulli. Yeah, there's nothing wrong with Bernoulli. Do you want to use Bernoulli? Sure. What do you assume when you use Bernoulli? This is very insightful, very enlightening for me. What do you have to account for to use Bernoulli? What? Invisible flow? Invisible flow. Do you want to assume invisible flow now?
No.
Moving forward? No, we grow older by a month. You know, you're more sophisticated. You are now dealing with viscous flow in chapter 8. Do you still want to use Bernoulli? If the problem didn't tell you that the flow is invisible, it didn't tell you. That's all it is. It didn't say anything about viscous or not viscous. What are you going to assume? Moving forward for all problems now. You better assume it's viscous. And it's the same in the test. If you're not told, you assume viscous. Only time you use Bernoulli is when you're told this, assume it's invisible. Okay, so make sure you know that very detailed because it can be a trap. So can you still use Bernoulli? No. Is it obvious it's going up or down? The answer is you don't know. You truly don't know. There's no way you can know unless you apply the energy equation. That's what we're dealing with in the next 20 minutes, 15 minutes, okay? So let me set up the example. I may or may not have time to go through that in detail, but it is enough for you to tackle the homework. I have a fire hose on a fire boat where I'm drawing water on a hose via pump. The elevation of the pump and the fire bowl is 2 meters from the water level. So it's a pump, and you are told the power. I use this nomenclature of outward-looking capital P. You're told that the power to run the pump is 35 kilowatts. The pump is perfectly efficient, no losses. Whatever power you put in go into moving the water. And I have a nozzle at the exit, which is 5 centimeters. That's what that is given. All right. it created water jet, which I can use to fight fire. And that's all there is given. Do you think you can determine on what is given, what is the velocity at the exit of this nozzle? I want you to think about the physics. Think about what assumption, if any, of you made, just from high school physics. How do you approach this problem? Is it actually uniquely and unambiguously determined? If I give you all of these, can you decide how fast the nozzle is ejecting water? Don't worry about how to tackle the problem yet. Just look at the big picture. I have a pump that control how much power to run it. I have a 2 meter elevation given the diameter of the nozzle. Yes?
Is the velocity on the bottom zero?
Bottom, which bottom?
Like at 0 meters?
Here?
Yeah.
What's the answer to that? Is the water velocity on this surface 0? Very fair question. What's the answer? Have you used this type of application before? In Bernoulli, say? What would be your conclusion about velocity here? It becomes negligible. At the water surface level, where it's atmospheric pressure, the surface area is so big, the velocity is negligible. Very good observation. What else? So what happened to the power from the pump? Maybe I can pare it down to something you can tackle. You have a pump that putting energy in electrical power. Yes?
Would the velocity be zero? Wouldn't we even know the size of the at the background level?
Do you need to know the size of the pump at the higher level? No, but I'm only dealing with the water surface in here, where the water is being drawn in from this large reservoir. I'm not focusing on the immediate intake of the pump. I'm looking further away from that intake at this free surface of the water. And from continuity, no matter how much water is drawn at the intake, when I'm far away from the pump, I don't see that. My velocity, because the infinite area is still negligible. Right? This is the same argument you use for Bernoulli. But we wouldn't want to use Bernoulli for 2 reasons. Tell me what are they? Viscous, now first of all, I didn't tell you this is a frictionless problem, right? And then, what else? You cannot use Bernoulli for a second reason. Permanent in the pump is chopping up the streamline. You can never follow a streamline, right? So the physics is I'm adding energy to the water to overcome what? To overcome what? Gravity or 2 meter, what else? Viscosity, very good, which for now, we were told that the friction effect, given in terms of an equivalent height, and we'll deal with that later, this is just the first step. To account for the friction in this pipe, you are not told what's the pipe diameter and how long, but you're given the equivalent frictional loss due to the water is equivalent to 7 meters of water. And we'll later on see how that can be used. So the pump work is being used to overcome elevation change of 2 meters, the friction, and what else at the end? What else? This velocity, if I make the nozzle smaller, the velocity go up faster. What has to be provided to make the jet shooting out like a cannon? Well, the kinetic energy of the jet, right? Do you see the physics? I have to pay a pump at 35 kilowatts to overcome the friction effect, the change in elevation, and the change in kinetic energy. And when I do all of that, it turns out this problem by way of energy equation is solvable. It's very doable, and that's what we'll do next. So the energy equation is given in a form that's very dangerous because it resembles the Bernoulli equation. So the energy equation, and I'll emphasize, not Bernoulli. For a general problem of what I call a flow system, my flow system consists of some plumbing and a device called machinery. Could be a compressor, a pump, or a turbine, where the work done is different. One is adding work, the other one is taking work from the system. By system, I don't mean a system control volume type connotation. System meaning a set of devices put together. And I have an inlet point and exit point with the flow direction, in this case, going from 1 to 2, which is different from your homework. You ask to know what direction they go. So with this picture, then my energy equation consists of the left-hand side